and they are anisotropic, A and B are anisotropic, then what? Then what would this lead you to conjecture should be true? If this was the best I could do, if this was the highest degree of non-uniqueness I could get, then you would say, then there exists phi such that A is equal to phi star of B. That would be the natural conjecture, because I showed you that for A, phi star of A has the same character denominator amount. Now you could ask, is that the only non-uniqueness? And that would be this result here. If this has a positive answer, it would say that if lambda A is equal to lambda B, then there is a diffeomorphism preserving the boundary so that one coefficient is a push forward of the other. Now this has actually been proven in 2 dimensions. And the way you can prove this in 2 dimensions is very interesting. There are 2 reasons that it works in 2 dimensions. The reason that it works in 2 dimensions is that the result is known in the class of L infinity functions. So you have it in all generality and you can go all the way down to that. But the thing that's also true in L infinity in 2 dimensions is that if I take a conductivity, so I have conductivity A, then I can find, in 2 dimensions, then I can find phi such that phi star of A is isotropic. So in 2D, given an A, I can find a phi star of A, a phi such that phi star of A is isotropic. Then you can see how it works, because then I can also find a C star so that C star of B is isotropic. And now you know that 2 isotropic, and they have the same Dirichlet-Ganoy-Mandel map. Now you know that 2 isotropic that have the same Dirichlet-Ganoy-Mandel map must be the same. So these 2 are the same. Well, then a simple calculus tells you that phi star inverse is just phi inverse star. So this thing here is equal to B. And then, of course, this is equal to phi inverse phi composed with phi star of A. And so you have your mapping that maps A to B. But the essential thing here was that you could find something in all these forward pushed, you could find something that's isotropic. And that you do by using a construction that's called isothermal coordinates. It's a PDE. You have to solve this in nonlinear PDE, and you find out that this has a solution by isothermal coordinates. And that does not, you cannot do the same in 3 dimensions. So this is actually true in 2 dimensions. So for my cloaking problem in 2 dimensions, I'm still in trouble, because it says if L lambda A is equal to 1, then there is a relation between these 2, and I can't do it for all A. So therefore the question is, what does that say about my cloak? It doesn't only have to be anisotropic, but it has to go outside the realm of the coefficients I've looked at here. What is it I've looked at here so far? I've looked at elliptic operators. And the only way I can go outside the realm of elliptic operators is it has to be anisotropic with degeneracy. And what does degeneracy mean? It has to have 0 and infinite eigenvalues. So it has to become a very degenerate problem. And now I'll go to the slides. Now I have 20 minutes, so please take that in the slides and I'll show you what because I think you're either too tired or too prepared for now having slides. While we're doing that, maybe are there any questions? Yes.
You're talking about when you have the non-data equal to the other, because with some condition of A and B, then you apply that the data equal to the other. And then instead you have the lambda A, for example, lambda A equal lambda B, and then you apply A equal to B.
In the isotropic category.
Yeah. So if they see the results, or for example, exterior problem, right? You can see the problem in embodiment outside something.
Well, but we know that if the solutions, the only way you can make the solutions the same in the exterior domain is by making the Dirichlet-Neumann data operators the same. Because otherwise there would be data for which the solutions were not the same outside. So it's equivalent. So we have to make the Dirichlet-Neumann data maps the same. Or like I would say here, that's the only way we can go with that. Okay. So let me, so this is joint work with Bob Cohn, Hoi Min Yin, Dan Onafry, who's also a postdoc of mine, I think Shen, who's a student of Bob's, and Mike Lumstein, who's it's very related to work of Greenleaf, Glasses, and Ullman, Greenleaf, Gorilla, Glasses, and Ullman, Hendry, Shurigan, Smith, and I'll actually first show you a very simple slide. This was actually the front of the Science Times, I think in 2007. I mean, mathematicians never get on the front of the Science Times, but physicists do. So this is a slide, and this is actually showing you. So it's showing you like a region like I have here. This is a closed. This is like fantastic. This is in a region where you can put anything you like, and this transformation doesn't get in there. You have a plane wave coming in here. So this is a plane wave, and you can see how it suddenly gets bent around that, and at a certain point it just snaps to the other side, and it exits at a plane wave to the other side. Well, here you cannot see this plane wave coming in here that is any different than the plane wave that had traveled all the way through. So that's sort of the idea of this, is have something in there. This is sometimes also, this whole area is called transformational optics, because the idea is to make a transformation in here that will make this kind of phenomenon appear, and that no information will be extracted from this domain itself. Okay, this was, as I gave you, this was the time harmonic Maxwell's equations. I derived that for you for the time frequency. And I said observable data is a Dirichlet-Neumann data map. And the thing is exactly to construct a subset D. This D here is now your set P2 of omega, so this ball of radius 2. Parameter, and parameters sigma and q. In this case, we've forgotten about q because we set frequency 0. So sigma, such that independently of what we put inside this object D, they are the same as for sigma is equal to 1, where also sigma q is equal to 1. And then we'll say that this domain in here is perfectly closed. And so this, in case here now, this is omega, this is your set D, and you want to construct parameters out here that makes this thing perfectly float in terms of the data that you have here. Simplicity, take omega is equal to 0, so now you have this exactly sigma is equal to 1 over here. You have sigma A is equal to sigma C, that's a cloak out here, C stands for cloak, and sigma A could be any A in here, so that's the same situation as I just said here. And you want to have the same voltage of F implies current plus G, and voltage F implies current plus G. You want to have the same Dirichlet-Neumann data map out here. That's exactly what I'm saying. Okay, this we can just skip. Here's now a transformation. So that's the transformation I want to spend a few minutes on. If you look at this transformation that I put on the slide there, what property does that transformation have? Well, that transformation has a property that, so f of x is 1 plus 1 mod x, 1 half mod x, x over x. It maps the ball of radius 2 with the center stemmed out to the ball of radius 2 minus the ball of radius 1. So this part here is mapped to this part here, and this is just 1 half x plus x mod x, right? Because when x is equal to 0, this is 0, x mod x puts you over here, and when x is equal to 2, this has length 2, this has length 1, this is length 1, and so 2 is mapped to 2 in an identity fashion. So this is just a way of taking the ball with a point stamped out and mapping it to the annulus. Okay, and then what you do is now you do the transformation I just did before here. This is what I call f star of sigma. That's the push forward of sigma by this. So you take sigma to be equal to 1 here, because that's really what you want. You want to make it look like coefficient 1, and then you take f star of 1 here. That's your flow. So, and now you have that L of 1, and L of sigma in general, but L of 1, the lambda 1, is equal to lambda f star. Okay? Now there's one thing here, and maybe I completely tired you out, but there's one thing here that is not quite true in what I'm saying, because I introduce an extra boundary here. What happened to the Dirichlet Neumann data mapping here? Well, that's actually what you will see is the Dirichlet Neumann data mapping here just disappears because it's 0. And so actually the only part of the Dirichlet Neumann data map that you pick up here is this one here to this one here. So this is actually true. But it's because this map here is very degenerate when it comes in here, because you're taking a point and you're expanding it. It's very degenerate in here, so that the contribution to the, when you're integrating by parts, disappears in here for the functions that you're interested in minimizing over. Not for all functions, but for your minimum, it disappears. So actually it is true that you have this thing here. But now, of course, you have to define what is f star of sigma. What the problem here is, and I'll show you, f star of 1 is very singular. F star of 1 here, it's 1, right? That's what 1 is. Over f star of 1, it's nice out here. But as you come in here, we know that f star of 1 is equal to d phi transpose over the determinant of d phi, opposed with phi minus 1. So we can calculate that as actually on the next slide. This is what it is. So I've calculated what f star of 1 is, and this is what f star of 1 is. Now, I didn't call these coordinates, so now I've actually called this coordinate z, and I call this coordinate x here. So therefore, you see down here, what happens is that when where is